Okay, so I'm doing problem number 51 from chapter 5. It says, an inventive child named Pat wants to reach an apple in a tree without climbing the tree. Sitting in a chair connected to a rope that passes over a frictionless pulley, Pat pulls on the loose end of the rope with such a force that the spring reads 250 newtons. Pat's true weight is 320 newtons, and the chair bears 160 newtons. Draw free body diagrams for Pat and the chair considered as separate systems, and another diagram for Pat and the chair considered as one system. Show that the acceleration of the system is upward and find its magnitude. Find the force Pat exerts on the chair. Okay, this is how I attempted the problem. So first of all, let's look at Pat individually. So we know that Pat is pulling up on the string right here. Right? So he's pulling down. So the string is going to be pulling up. So there's a tension that's acting over here. And they tell us that the magnitude of that tension is equal to 250 newtons. Let's see what else they gave us in the problem. They told us that Pat has a weight of 320 newtons. So we know that Pat's weight is acting downward from here with a force mg equal to 320 newtons. Now, since Pat is sitting on a chair, there also must be a normal force between him and the chair. So, since we know that the normal force must be acting upwards, let's just call this FNCP, meaning that the normal force that's acting from chair C onto Pat. Now we need to draw a free body diagram for the chair itself. So let's say this is its center of mass. So there's its weight that's acting downward. So let's call it M chair G, which they told us is equal to 160 newtons. So coming back here, we know this is equal to 160 newtons. Now, if you look at our free body diagram with Pat, we know that the normal force that's acting on Pat by the chair is FNCP, right? But Newton's third law tells us that for every force there is an equal and opposite reaction. So Pat must also be exerting a normal force on the chair. So let's call that FNPC, meaning the normal force that Pat is exerting on chair C. Now, if you look at the setup over here again, the rope is also pulling up on the pulley right here. It's also pulling up on the chair right here. So what that is going to do is these two strings, there's going to be a net tension pulling it with a force of 250 newtons. Which is obvious since we know that the tension acting on both sides of the string must be equal. Now finally, let's look at the combined system. So this is basically what's happening in the entire picture. We have Pat sitting on a block. He's pulling down over here on the string. So the string is in turn pulling him up there. And then, since the string is pulling up from here, it must also be pulling up from here. So if you look at this, we see that the net forces acting in the upward direction is this tension and this tension. And the net downward forces are the force of the weight of the chair, and CG, which is equal to 160 newtons, and weight of Pat, which is equal to 320 newtons. Now note that it did not include the normal force over here, because since one is pointing up, since it's an internal force, we don't really need to consider it when we're only dealing with how the system is moving as a whole. However, we will need it when we're finding the individual acceleration of a single object. So there are two ways how we can approach this problem now. One, like I mentioned here, we can just basically consider this entire thing as a system now. So let's say this is just one object. And on this new box, there's a force of 500 newtons upwards and 480 newtons downwards. For the mass of the system, we simply add up the masses of Pat and the chair. So mass Pat plus mass chair, which is simply equal to 480 newtons over G. Now we can use Newton's second law and sum of the forces in the y direction. So this would be equal to the net force upward, which is the tension from rope 1, so Ft, plus the tension from this rope right here, so again Ft, minus the weight of Pat and the chair combined, so minus weight Pat minus weight, and this should be equal to the mass total times the acceleration. Now we already know that this is equal to 500 newtons, since we know each of them is 250 newtons each. And we already found that the total net weight acting downwards is 480 newtons. So that's 480. Their total mass, like I mentioned before, is 480 newtons divided by G. Now to solve for their acceleration, all we need to do is rearrange this equation and solve for A. So if we do that and plug the numbers into the calculator, we find that the answer is equal to approximately 0.41 meters per second squared. Oh, now note that I forgot to mention this before, but let's just call upward motion as positive. So this acceleration is also pointing in the upwards direction. So now we've already shown that the system as a whole would be moving in the upward direction. Now, if we need to find the individual force, the forces that is acting between Pat and the chair, what we do is we use Newton's second law, but this time we only do it for Pat. So now if you look at all the forces acting on Pat, we know there's a tension that's pulling him upwards, there's his weight which pulls him downwards, and there's also the normal force which the chair is exerting on him, but we don't know the magnitude of. So if we write Newton's second law for this direction again, we find it's equal to tension plus Fn Cp minus his weight, and this is equal to the mass times acceleration. Now we already know what the acceleration of the whole system is. But if Pat is moving with the whole system, then his acceleration must also be equal to that of the system. So for A, we can simply plug in 0.41 meters per second squared. For tension, we know it's 250 newtons. His weight is negative 320 newtons. And now we just need to solve for force normal. So if we rearrange the equation for normal force, we get that it's equal to 70 newtons plus mass times the acceleration. Now to find the acceleration, all we need to do is take his weight and divide it by gravity, right? Because weight is just mass times gravity. Now, if you plug these numbers into the calculator, we get the answer as 7. So we get that the answer is equal to approximately 83.39 newtons. So that's the force that the chair exerts on Pat.